Okay, so the first rule we're going to look at, the rules for adding and dropping quantifiers, is universal instantiation. And that is the rule called UI. And it's easy to use this rule because of that basic fact number 1 from predicate logic, that a universally quantified sentence is the same as a big conjunction where you replace the variable by the names of the objects in the universe that X picks out. So since this is a big conjunction, you could simplify out any one of these terms. Remember, that is equivalent to that. And since this is a conjunction, you can simplify out any term. So if you start with, as your premise, that, you can use UI to get rid of your quantifier and replace the X by the A. Because remember, that expression, i.e., that expression is equivalent to this. And so you can simplify out any component. So instead of replacing this by an infinitely long sentence, UI tells me I can simply simplify out any one of the terms in this infinitely long expression and put it here. I could do that. These are all correct. I can get rid of my quantifier and change the X to any name in that universe. But I can do even more. If I don't want to use names, I can keep that as an X. And if I want to change the variable, I can. Every one of these moves in this proof are legitimate. So that tells you UI allows you to do almost anything, except for the following. There's one thing you can't do. And it is the following. If you have a matrix with 2 occurrences of the same bound variable, then when you do UI, whatever you do to the first occurrence, you have to do to every other occurrence as well. So this is good. That's good. And it makes sense because that is good. This also is good. This also is good. But now let me show you something bad. This is very bad. Notice what was done. X was kept as X. The other occurrence of the bound variable, the other X, was changed into Y. You can't do it. Now, just being told you can't do it really isn't enough. You really need to understand why can't you do it. What bad things could be the result of doing this. And I'll tell you, the bad things are unbelievable. I'll be dramatic. You would not want to live in a world where this validly followed from that premise. Here's why. Let's focus on this, and you haven't learned how to add quantifiers yet, but let's suppose we do. Okay, if line 4 validly followed from that premise, then you could validly infer line 5 and then line 6. And that's the disaster. If line 6 validly follows from this premise, the world would have to be so strange that I myself would not want to live in it. But let's pay attention to what this sentence says. The first sentence says, everything in our universe is such that it has this property. It's either F or M. What does this say? This says, look at every pair of objects. The first one from X, the universe picked out by X. The second one from the universe picked out by Y. Let's assume X and Y pick out the same set of objects. Then what this sentence says is for every pair of objects, the first member has F or the second member has M. Now let's restrict the objects to be people in this room. And the property F will be female, and the property M will be male. So premise 1 says, all the people in this room are either males or females. Fine, that's true. But number 6 says, for every pair of persons in this room, the first member of the pair is a female, or the second member is a male. Well, let's see if that's true. I'll just take an arbitrary pair. You're the first member, I'm the second member. Okay, first member is a female. True. So since it's a disjunction, a wedge, it's true automatically, since the first member is true. We don't have to look at the second. Okay, next pair. You'll be the first member, I'm the second. First member, female. True. Okay, it's true. Well, what's the problem, Professor? I said every pair. So the pair where you're the first member and I'm the second member, and there's also a pair where I'm the first member and you're the second member. Let's look at that pair. Okay, the pair where I am the first member says female, but I'm a male. False. Well, let's look at the second member. It says male, but you're a female. False. So that would show this whole sentence is false. But if it validly followed from this premise, it would have to be true, meaning our world would have to be such that one of us changed sex instantly. But, and here's the hard part, remember, there are going to be pairs where you will need to be a female to make that thing true. There are other pairs where you'll have to be a male to make that true. So you would have to be in a quantum superposition of being a male and being a female. You couldn't just be a weird new sex, male and female. That wouldn't work. You would have to be both male and female, but not male and female. And the only way that can happen in the macro world is if you're in a superposition of both. but quantum properties don't happen at the macro level. So we would all have to violate quantum, the classical mechanics. We would all have to be in quantum superpositions of male and female in order for this sentence to be true. I can take any set of properties. It doesn't have to be male, female. We could divide the objects in this room into humans and tiles, ceiling tiles and floor tiles. And then the problem would be, if this followed from this, that we would have to be in a quantum superposition of being human beings and tiles. Would you like that? Who would like that? To be part tile and part human? Or part, we could change it, PC. We would have to be part human and part PC. Or paper. We could change it so we'd have to be part human and part paper. So it's a simple rule. When you have a universally quantified sentence with multiple occurrences of the bound variable, if you do UI, whatever you do to the first occurrence, you must do to every other occurrence. You can't treat them differentially when you do UI. And that's it.